Hi everyone, I'm back after a long break and today we are talking about grayscaling algorithms in C. So let's say I've got a grid of pixels like this. Each one of those pixels is going to have a specific color. So here I just drew a smiley face, but if I was to examine one of these pixels, let's say the orange one right here, the RGB value is 255, 192 and 0, right? And if I was to take this eye color right here, that would be 0, 112 and 192. So each pixel in this image has an RGB value to describe the color. Now let's say you wanted to take this image and create a grayscale version of it. How would we do that? Well, as it ends up, there's multiple algorithms we could use to convert these pixels from RGB into a grayscale space. And the three most common ones are called the average method, the lightness method, and the luminosity method. So let's go through each one of them one by one. With the average one, we take each component of the RGB values, so red, green, and blue, and then divide that by 3. So if we were to take that orange pixel right there as an example, the red would be 255, the green would be 192, and the blue would be 0. So if we add those three together and then divide by 3, we get 149 as the grayscale image, the grayscale value. So the image, the pixel color there would be 149, 149, 149. That would be the grayscale version. Now, if we were to use the lightness version, we would take the max of the red, green, and blue, and then we take the minimum of the red, green, and blue. So we're going to find the maximum of those three values and the minimum of those three values. Then we'll divide those two numbers by 2. Or we're going to add them first, then we're going to divide by 2. So here that would be 255, which is the biggest value, and then 0, which is blue, is going to be the smallest value. We add those two together and then divide by 2, which gives us 127. Now the final method is luminosity, and it's got this weird formula right here, which is 0.21 times by red, 0.72 times by green, and then 0.07 times by blue. Then we add them all up. The idea behind luminosity is we're going to take our RGB values, or let's take a step back. There's multiple representations of color space, right? So RGB is just one of them, using red, green, and blue. Another one is called HSL, so hue, saturation, luminosity. What this formula does, it converts our RGB value into HSL space, and then we take out or isolate the luminosity value. So it's going to perform that transformation, and then it's going to give us back the luminosity value, which will be in grayscale. So in this example, that's going to be 0.21 times 255 plus 0.72 times 192, and then 0.07 times by 0. It's going to give us 0. And that's going to give us a value of 191. Now, the thing I want you guys to notice is that despite us having used the same original colored pixel, when we apply these grayscaling algorithms, we get completely different grayscaled values. So even though we have the same input, depending upon the algorithm, we can generate a different output. And the idea is, depending upon the image, you might want to use a specific algorithm because it will produce the desired effect that you want. So that's it for the theory, and now we're going to write. So I'm here in my code editor, and I've just got a basic hello world program set up here, and I can compile and run it. I've also got this folder called images, so if I just see what's in here, we've got this image right here called field image. So if I open up in Explorer, it's just this image of a field. What I'm going to do is I'm going to load in this image, then I'm going to generate 3 grayscaled versions of this image using the average, luminosity, and lightness algorithms. Then we can compare all 4 images and see how they look a little bit different from each other. So the first thing we need to do is actually load in the file. Now, how we're going to load in the image file. So it's a JPEG file, and I could go through and explain to you guys how to load in a JPEG file, but it's quite complicated. So instead, we're just going to use a simple library just to get it done for us. So we're going to be using 2 libraries today. We're going to be using the stbimage.h and the stbimagewrite.h libraries. So these are header only libraries, which just means you can copy and paste this header file, then include it, and you can just use it right out of the box, and it compiles extremely fast. So I'll leave the links to these 2 libraries down in the description. And once you've copied and pasted both of them, so I've done it right here in my source directory, I've got the stbimage and the stbimagewrite libraries. we can then include them. So in order to do that, we first have to, well, let me just open it up. We can read the documentation just to see how to load them. That's a bit weird. Right, so first we have to define this macro called stb image implementation. What this basically does is, why isn't it copying it over? Okay, there we go. So when you define this stb image implementation, it will, or normally, let's see what happens if we don't include it. What's going to happen is, so when we just include the header file, it just writes down or copies over the structs and the function declarations. It doesn't actually copy over any of the function definitions. So if you've got multiple files you want to control where the definitions go to, like in a separate library, then it makes sense just to include it, just to include the header file without this macro. But when we include this macro, it will include the function declarations and definitions along with the structs. So we got everything there ready for us to compile. So I'm going to include that for this thing right here, and then the stb image write.h, I'm going to do the same thing, but we're gonna have to just copy over this macro, and then it's gonna be stb image write. That should be good. Now the next thing you have to do is actually load in the image. So if you go to stb image.h, we've got a function down here somewhere called stbi load. There we go. So the way it works is, let's just copy this over and then we're gonna go through all them one by one. Okay, so it's gonna, if you look at the declaration, you have to pass in x, y, comp, and required comp. So it's pretty simple. They just describe the parameters right here. So x is the image width. It's gonna be a pointer to the image width. So it's gonna load in the image for us, depending upon the file name right here. Then it'll write down the image width into this x variable. Then this image y into this y pointer. The number of channels in the file into this and value here, and the desired channels is going to be 0. So we can specify a number of channels. For example, if we want to be like grayscaled for us, we can pass in a specific flag through the desired channels. If we just do 0, it's going to load in the number of channels in the image, which is what we want, because we are going to grayscale the image ourselves. So I'm going to turn this into a uint8t pointer. So unsigned char basically means uint date, so we can just use this variable directly instead if you include this header file. And then I'll change xy, so I'll do width, height, and number of channels. So we just do that. Now the other thing we have to do is, once we finish using the image, we have to free the memory. So we'll just do that right here. Let's do free data. And we'll just check is the values of width, height, and number of channels, just to see if it loaded it in correctly. Sorry about that, it's a bit weird. Oh, there we go. I was trying to put in a backslash, then it just went to a different file instead. File name undeclared. Okay, we need to. So what's it called? Images, and then it's called fieldimage.jpg. Then we have to do that. Okay, and it loaded in the file correctly. And we can also verify that the pointer, it's valid, because if it's equal to null, then we've got an issue. Yep, it loaded in the file. That's great. So now that we loaded in the file, we can then just create the grayscale versions of them, I guess. So the first thing we have to do is allocate some memory to actually store the new image. So what we can do is, let's say we'll do uint8_t, we'll call it grayscaled, let's say average first. So we do average image, that's going to be uint8t. Actually, we don't have to even allocate, we have to do that. We can just do malloc, so we have to include stdlib to use that. So we can malloc some memory to store the image. So we say width, height times number of channels. So width and height is the number of pixels, so vertically, so number of rows and number of columns in the image. Number of channels tells us the density of each pixel, so how many values you store in there. So usually that's going to be 3, right? So that means 3 means RGB, right? So it's going to have 3 values for each pixels, or rather, one uint 8 for each component, so RG and B. And we can do the same thing for the other 2 images, or other 2 algorithms. So we say lightness, and then we can also do luminosity. How do you spell luminosity? Right, so we've got all 3 of them. Now the next thing we have to do is just iterate through this data array, and then we can just look at each pixel, the RGB values, and then calculate the average, these 3 different values from it. Now how are we going to iterate over the data? Now the thing you have to understand is this STB library is quite nice because it gives us back this array of the data and is organized in this way. So it's going to be a flat array of size width times height times number of channels, and it stores the information like this. It's going to be a uint 8 for each of these values. So it's going to be an R value, a G, then a B, then the next pixels R, G, and B, R, G, and B. And each one of these RGBs represents one specific pixel on the screen, right? And each uint 8, so like 0 to 255, that's the range of uint 8, which is, or 256, I think? Yeah, 256 or 250, one of these two, 256, 255, which is the range of the range of each individual component of RGB, right? Because this RGB each of these values can only be in the range of 0 to 255. So we're just going to have to loop over the width and then the height, and then we can extract each single component from there. So we can do something like this. So we say for int y is equal to 0, y is less than height, we say y plus plus. Then for int x equals 0, x is less than width, we do x plus plus. And then there's a few ways we can extract the RGB values. So we can first just calculate the index, which is going to be number of channels times by y times by width plus x, and then we can extract the actual pixel from there. Now you might be confused what the heck's going on right here, so I'm going to explain it. So the way it works is we have it organized in rows. So we have, like, let's say pixel equals, let's say P is a pixel is equal to RGB, right? So 3 uint 8s together, and then we have them organized like P, 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 P. Let's copy this. So we're going to have the number of pixels, so the number of columns is going to be equal to height, right? And then the number of rows is going to be equal to width. No, I did that wrong. So the number of, I need to think through this very carefully before I start saying. So number of rows is equal to height, and then the number of columns is equal to width, right? So let's say we are at 0. I'm trying to get this pixel right here, the 4th pixel. So y is going to be 0, and then x is going to be 4, right? So what we have to do is basically take the y value times it by the width, which in width is going to be, let's see, what is it, 4,000. So this is we're gonna jump 0 rows, and we're gonna add 4, which is gonna be x to get this thing. Let's say we want to get this pixel down here, so 3rd row, 2nd pixel. So that's going to be 2 rows down, then 3 pixels across. So we're gonna do y, which is 2, times by width, which in this case is gonna be 6. So 2 times 6 is gonna bring us 12 down here. We're gonna add the x, which is the one that we want to get, which is gonna be 3. So 12 times 6 times 3 plus 3 is going to give us 15, which is the index of this thing right here. Remember where I said it's a flat array, so we just treat them all like that. So we're going to take this flat array and try to index specific pixels by doing that calculation. And then we just times this by number of channels, because remember, this is a uint 8 array, and then each pixel is going to be 3 components, so 3 uint 8s RGB. And then that's going to give us an index, right? Then we can take this index, or this pixel index, and that's going to be a pointer to our pixel. So it's going to be a pointer to, let's say, let me put this back here. So let's say we got this 15 as the index. That's going to be a pointer to this pixel right here, which is going to continue on. So we can just read out the RGB values by doing this. So we can say R is equal to pixel at 0, right? Unit 8 underscore T. G is equal to pixel at 1. Unit 8 T. B is equal to pixel at 2, right? So because index is right here, this is going to be 0, 1, 2, because we're just moving in unit 8 increments across. And then we can actually just print out pretty much all the pixels in the screen. We can do that literally right now. So let's say, I'm not sure exactly what the specifier is for unit 8, but this should hopefully work. And there you go, we're just printing out all the pixels in the screen, the RGB values. So what we now need to do is, let's say we do the average method first, right? So we can do unit 8. Let's calculate the average pixel. So unit 8t average. It's going to be pixel at 0 plus pixel at 1 plus pixel at 2. Divide that by 3. That's going to give us the average value. And then you can also just do the other two, which is going to be grayscale or lightness. And then we can also do luminosity. So actually, we'll just do RGB. Luminosity, the formula, remember, if you can remember it, is 0.21 times by R plus 0.72 times by blue or G, green, plus 0.07 times by blue, so B. For lightness is going to be the maximum, so max of RGB minus or plus the min of RGB divided by 3. So we need to create some kind of function or macro in order for us to find the maximum minimum value. So there is a pretty cool macro we can do. So let's say we have a macro here called max. Let's say we give it two values, I don't know, x and y. And then we can use the ternary operator to say, okay, if x is greater than y, return x, otherwise return y. That makes pretty much sense, right? So if I had something like 5 is greater than 3, return 5 else 3, this is going to evaluate to 5. If I was to instead put like a 1, I put 1 here, it's going to return a 1. Oh, right, let me just put it this way. Yeah, so if I had 1, it's greater than 3, return 1. Oh, so it's going to return a 3. That's the way it works. So I can build up using this macro. So I can do max of 3 instead. So I do max of x, y, and z. So what I really have to do is just find out the max of, let's say, let's think about this. So we do x right here, then max of y and z. So you find out which one of y and z is biggest, and then we compare that to x. That's going to give us the biggest value out of the three. So let's say z is the biggest. This is going to evaluate to z, then x and y we get z. If x is the biggest, it's going to evaluate to this, and if y is the biggest, it's going to evaluate to this. And we can also just do the same thing, but instead with min. So we do min. So instead of doing comparing which is going to be greater, we can just flip the sign right here, and then we just do min 3, and then we do min 3 once again. And that's pretty much it, right? And we've got two macros to find the maximum minimum. And if you guys don't believe me, we can just do something like, let's just delete all this for a second. We'll do printf maximum, let's say max 3 10 5 3. And you got, as you can see, it was, let me just put a new line. Okay, so it always prints out 10, doesn't matter which order we put it in. And then we'll just do min instead, and this should always print out undeclared call to That's a bit weird. I defined it right here. I'm not sure what's causing the error. We just defined it right here. Let's see. Oh, okay, it should be min there. There we go. So it prints out 3 as well. So as you can see, it does actually work. I wasn't just making things up. We've got to fix that error. Let me just undo all of that. That should be min, and that should be min as well. So there we go. We can calculate the max of the 3 and the minimum of the 3. Then we've got the average. We've got its average value, right? So all we have to do is going to replace this pixel's RGB value with average, right? So like all RGB is going to be replaced with just this average. Is the same for these two. So we can just instead just say, let's say memset grayscaled average image. So right, this image right here, we're going to set it at plus index, because remember these buffers and this buffer data are both the exact same size, so we can use the exact same indexing as well. So we can do average and then we'll just say 3. Basically what that means is at this pointer right here, which is going to be a size of unit 8, copy this value and copy it 3 times. So unit 8 increments 3 times. And then we do the same thing for the other 2 images. So we do lightness and then lightness right here, then luminosity, okay, there we go, and that's pretty much it. So we got, let's see, so all we have to really do now is just save these images. So we've got these buffers with the new image, and then we can just save them. So first, before we do that, let's do this here. So to save the image, you have to use stbi image write.h right here. And then if you just look here, let's say we want to do a JPEG because it seems to be the simplest, and that's also JPEG doesn't have any transparency, so we can just use RGB like we have right here. Just copy and paste this thing right here. So it's just going to be a success flag for us. And then first we have to put the file name. So I'll say for this one, images, let's say grayscale average.jpg, and then you can pass in the width. So the width's going to be the same as the original image, which we got through the pointer. So we just say width, height, then components. Its composition is going to be number of channels, so RGB, right? So this is actually going to give us this is giving us an RGB value. So you know, it's grayscale, there's grayscaling in the RGB space. Then a pointer to the data, which is going to be grayscale average image, just the point to the buffer, and then quality, which is going to, let's look at the docs. Let's see what the quality flag actually means. So let's see. Quality is between 1 and 100, so we're going to say 100 for the highest quality. And there we go. So then we can just do this for all 3 of them. It's going to write 3 images. So we say lightness and then luminosity. Let's see, grayscaled average image. Oh, I forgot the D at the end. Okay. So if you just go through all of these and then just print out if successfully saved the file or not. So you say if success average, successfully saved like average file, else printf failed to save average file. Then we just go through each and every single one of these and just print out the status of each of them. So we say and then you might be saying, okay, so we should free the buffers here, right? So like free grayscaled average image, and free the other files, the memory we allocated before. That's not actually needed because once we exit the program, the operating system has to free the memory for us. So since its memories existed for the lifetime of the program, we don't really need to worry about freeing it explicitly. The operating system should free it for us. So let me just fix the indenting. So now we compile the code, then fix the images directory, just that. Let's run the code and take a little bit of time. So it saved all files. So if we do images, let me just open it up. So here we go, we've got all 4 images. I'll do something like this. So actually 1 second, let's see if we can get this to work. So okay, that's gonna go there. That's gonna go here. I'm trying to figure out a way to get all 4 on the screen if Windows lets me. And then we can get this one right here. Okay, so we got, this is all 4. So this is the original image, this is when we use average, this is when we use lightness, and this is when we use luminosity. So all 3 of these images which we generated are grayscaled, right? But depending upon the algorithm we used, we can get a slightly different look. So this one looks pretty normal. This one looks a lot more lighter and detailed. This one looks a bit more darker and less detailed. I'm not an expert in which one you want to use for what. It just depends on the application, but it's pretty cool how we can just take one piece of data and apply it a slightly different calculation and get an image which looks very different. So that's pretty much it for today's video. In the next couple of videos, I'm going to show you guys how we can speed up this process of grayscaling a image. So we're going to use things like SIMD vector operations to speed up on the CPU, and then I'll also show you guys how we can use CUDA in order to do this processing on the GPU to make it even faster. So I hope you guys enjoyed the video. Please like, comment, and subscribe. And if you've got any more questions or future video ideas, please tell me. Thank you for watching.